Welcome back, students. We're in lesson 20. Video A, it's going to be a t-test for mean. So we've done the intervals, now we're going to run tests. Quantitative data summarized with the mean. Let's run a hypothesis test. Official steps plus an example. This will probably be a longer video. I don't know, 26 minutes I'm going to guess. Official steps to run a one sample t-test for a mean. So think about this. We're testing a mean. We have one sample of data versus a number, a hypothesized value. And because we're working with means and we're using the standard error, it is a t-test because we're using the student's t distribution. Write the hypotheses. We always assume equality up in the null. Just be careful and put mu. Do not put p here. So the null hypothesis. H sub 0. Mu equals mu sub 0. Mu sub 0 is just going to be a number, depending on the context of the problem. Just some value that we're testing against. Alternative hypothesis, H sub A. Again, it's going to be mu. And then you read the problem. If the problem says less than, it's a less than test. Different from, not equals to. Right? So nothing really new here. It could be less than, greater than, or not equals to. Same old number there. Okay? And it's not all three, it's just the one. Check those conditions, step 2. Very important. If the conditions are not met, then the statistical methods aren't going to work the way that they're supposed to. So, number 1 up top, the variable is what, and we're working with means quantitative. It's always step 1. What kind of data are we working with? So the variable is quantitative. The sample is random, which is harder to obtain, or at least unbiased. So we've got to have a good sample. We would really prefer a random sample, but at least unbiased, to be sure. Sample size n is less than 10% of the population size, big N. It's the same as always, right? And the sample size is at least 30, because we're working with means, so the magic number we've said is 30 is about right. So the sample size is at least n equals 30. Or there is strong evidence that the population is normal. If you have a small sample, say 18 values or 21 values, which isn't quite close to 30, then what you want to do is take your data, graph it with a histogram, take your data, graph it with a QQ plot, and look for evidence of normality. Unimodal and symmetric shape, and then with the QQ plot, points on the dotted line. All right, so that's step 2. Get those conditions. Step 3. Run the test, and there's 2 steps as always. We'll convert the data to a test statistic, which will be a t because we're running a t-test. Let's get the formula here on the board. First, convert your data to the test statistic. It's a t. T will equal, I'll take y bar, I will subtract off mu sub 0. So this is a sample mean. Subtract off the hypothesized value, and divide by s over square root of n. This thing will have degrees of freedom equal to n minus 1. So remember, when we're working with the t-model, there's a bunch of t-models, one for every degrees of freedom, and so we'll need to know basically sample size and subtract off 1. Okay? This should look familiar. It should look sort of like a z-score, right? I'm subtracting off the hypothesized mean. I'm dividing by a standard deviation or a standard error. And so this test statistic can be interpreted as if it were sort of a z-score. How far is my sample mean? How many standard errors am I above or below the hypothesized value? Once we get that test statistic, we need to convert to a p-value. So second here, get the p-value by shading under the student's t in the HA direction. If you're doing a greater than test, you shade up. And if you're doing a less than test, you shade down. And if you're doing a two-tailed test, you shade both ways. So over here, get the p-value Here's a t-curve with degrees of freedom equals n minus 1. Do not draw a normal model here. If you drew a normal model, erase it and start over and draw yourself a t-model. That's a joke. Centered at 0. Let's say I'm doing a greater than test. Maybe my test statistic t falls out here in the upper tail. I would shade this. The shaded area, just like for our z-test, is the p-value. And how do we get that? Well, on StatCrunch, it's the t-calculator. So on StatCrunch, you could use the t-calculator to determine that. And it's really simple. You just type in degrees of freedom and sort of change to the greater than sign and just plug in the number and it will draw the picture and shade it. Okay? As always, if the p-value is small, we reject the null and so on and so on. 4 and 5 here. 4, make your decision. If the p-value is, quote, small, reject the null in favor of the alternative. On the other hand, if the p-value is large, fail to reject the null. Number 5, write a concluding remark based on your decision in the context of the problem. We've done enough of these, so if you're competent in running a hypothesis test, now it's just a small change and everything else is the same. Okay. Let's do the example. 154 MAT127 students filled out a survey at the beginning of a recent fall semester. One question asked of the stat students was, how many credits are you carrying this semester? Okay. Presuming Math 127 students are representative of all Cecil students when it comes to credit load. So that's the unbiased sample. Can I reasonably assume that stat students carry about the same number of credits on average as the general population? I don't see why that wouldn't be the case. I mean, it's not a random sample taking just Math 127 students, but we're going to go with it. Do we have very strong evidence that Cecil students are, on average, below full-time status? So full-time status is 12 credit hours at this school, and so let's take a look at some data here. Summarized data is below sample size. N is 154, right? Sample mean, there's the value of y bar. From the sample, it was about 11.5. Are you convinced? Does that 11.5 convince you that for the whole college, it's under 12 credit hours? I don't know. I really do have to run this test. I mean, it's half a credit below, right? Is that statistically significant? Standard deviation, here's S. The range was 18 credits. Minimum was 4, max was 22, and there's the rest of the summary statistics. I'm noting here the sample size is above 30, so even if the data looks skewed, I'm covered. I have a big enough sample size, and I can proceed with the test. All right. You can see the histogram here. I suppose unimodal, but it's skewed, right? This doesn't look symmetric. There's a bit of a tail there off to the left. It kind of goes up more and tails off. So good thing we have enough data, but we can proceed with the test. Always good to graph it. Take a look. Try to understand what the data is telling you. And even more so, before you run off and do the test, look at the summary statistics. Try to get a sense of what the data is telling you before you do the official hypothesis test. All right, we're going to go through, I've got the 7 steps here listed out, sort of baby steps for this first example. Read and understand the context of the problem. Is the variable categorical or is it quantitative? Are you working with proportions or are you working with means? Are you dealing with 1 or 2 samples? Well, it's credit hours, which is a quantitative variable, so if I take the lazy man's way, I'm just going to circle what it is. Quantitative. Quantitative, certainly we're working with means, and I just have 1 sample. It's not as if I'm comparing, say, younger students to older students who's carrying more credits, or males versus females. That would be a 2-sample problem, and we'll get to that. So this is definitely a 1-sample problem for means, and the data is quantitative, so we're going to run a t-test. And of course we are, because, well, we're in the t-test chapter. That's what we're studying here, so it's kind of obvious for that reason as well. 2 and 3, write down the hypotheses, check the appropriate conditions before proceeding. So, the question had asked, in that paragraph, do we have very strong evidence that Cecil students are on average below full-time status, and full-time status is 12? So, H sub 0 mu equals 12 credits. Do I have evidence that Cecil students are below average, less than 12 credits? Make sure it's mu, not p. We'll take a point off, and then you'll get mad. So put the right symbol here, okay? And put the units. I really would encourage students to put the units. It just helps us remember what we're working with here, that it's not a percentage. Conditions. All of those things. Yes, the variable's quantitative. It's credit hours. What else do we need? We were told that the sample was unbiased or random, 154. No, it was the stat students, right? So we do have to presume. We do have to presume that math 127 students are unbiased with respect to this problem, with respect to credit load. Okay. The sample size n equals 154 students. Yep, certainly less than 10%. This is less than 10% of Cecil's population. And number 4, do not tell me 10 successes and 10 failures. You'd be in big trouble. Sample size was 30 here, right? So n equals 154 exceeds 30. So on your page in the notes, this is 2 and that's 3. Just trying to save a little space on the board here. All right. Looks like everything's good to go to run the test. You'll see just how easy this is. So it's number 4. Based on the collected sample, convert your sample mean to a test statistic. Let me just see what this next slide looks like. All right, I'm going to put these side by side. I've got enough space. So for 4 here, test statistic. The formula is a t. It's y bar minus mu sub 0 divided by s over root n. And the numbers come from the summarized statistics on the first page. So this is going to equal sample mean, 11.565. Subtract off 12, hypothesized mean, and divided by 3.749. That's the standard deviation over square root of 154, sample size. This equals, and it'll be negative, and that's fine because we're below average. The mean is under 12. This is negative 1.440. And when you're working with t, to make sure you get the right t model, you do need degrees of freedom. It's the sample size minus 1. You can check me on your calculator at home, but it's 153. I promise you. Okay, if you flip the page, it says to determine the p-value. We'll just do it up here in the corner, get the p-value. All right, here's a t-curve. Degrees of freedom, 153, centered at 0. Do not draw a normal model. If you drew a normal model, erase it and start over. That's a t-curve. I'm going to put my test statistic here. It's below 0. I'm off in the left tail. I need to find the shaded area here. That is the p-value. How do I get that? Here's what you're going to do. Go to StatCrunch. Go to the calculators. Pull up that t-model. Put degrees of freedom, 153. Put the test statistic as the shade below. Change it to less than, because I'm shading down, and hit go. I know you can do it. I'm not going to even switch it and show you. I'm so confident that you could do it. And so this turns out to be, let's see, the p-value in this problem is 0.076. Okay, and that came from StatCrunch. I use the T calculator on StatCrunch to get that value. All right, and you can do it too. I know it. So this is one of those screwy p-values. It's sort of right in the middle of the gray area. And like I was saying, boy, I need to run the test because is 11.5 credit hours, is that far enough below 12 to convince me that on average our students are below full time? And now I've got this screwy p-value that's ambiguous, right? It's kind of like, do I reject or don't I? I don't know what to do. But let's see what I'm going to do. Flip over to, let's see, 5 we already did to determine the p-value, and so 6. If the p-value is small, reject the null in favor of the alternative. If the p-value is large, fail to reject and write a concluding remark. My thought is fail to reject. I usually prefer my p-values to be super low, at least below 5%, before I really feel good about rejecting. I'm curious what I thought when I wrote the answer key up here to these notes. Problem asks for very strong evidence. 0.076 is not very strong evidence, right? So recall back in the beginning here, the problem asks for, and it did say it, and I remember now, it asks for very strong evidence. Very strong evidence is more like p-value way below 0.05, right? Below 0.01 even, extraordinary evidence. So with a p-value of 0.076, I would say that if we've got to make a call here, the call is fail to reject. Check that p-value chart. I have no idea what page it's on, but it's in the lesson where we did proportion hypothesis tests, and it's towards the beginning. P-value is not very strong evidence here. Fail to reject, and I guess what? We're not convinced that on average Cecil students are below full-time status, right? So because we failed to reject, we're not convinced that on average, this is covering, remember we're doing a problem about means, and so the on average part's sort of covering that. We're not convinced that on average Cecil college students carry a below full-time credit load. Right? We're not convinced that on average Cecil students carry a below full-time credit load. Right? And that's 12 credit hours. So we didn't prove that they carry a full-time load at least 12 hours. There was just not evidence to the contrary. And there is a difference between those two. All right. I think there's one bonus question at the bottom, and then we'll wrap this one up. If we made an error, bottom of that page, what kind of error did we make, and what on earth would that mean in the context of the problem? It all depends on what we did. And what we did was fail to reject. If we made an error. Big emphasis on if. Students sometimes get the sense that, oh, after I ran my hypothesis test, it's like a coin flip. Either I made an error or I didn't, must be 50-50. That's not the case if we made an error. So, since we failed to reject HO, we could have made, it's a type 2 error, we could have made a type 2 error. And what the heck does that mean in the context of the problem? We failed to reject, but we should have rejected because we made a mistake. We should have rejected. So this would mean what? In reality, at Cecil, our students are on average below full-time. This is what this means. In reality, at Cecil College, our students are, on average, below 12 credit hours. In reality, at Cecil College, our students are on average below 12 credit hours. We concluded, hey, there's no evidence to say that, but we made a mistake. And I'm not saying we made a mistake, I'm saying there's a chance. To calculate the chance of making this mistake is a bit beyond the scope of a Step 1 course. Okay, so we're never going to really be able to put a number to this. If this was a type 1 error, we could put a number to it. I mean, if we rejected and we knew that p-value, I could figure out, hey, what's the probability I'm making this mistake? And it's probably going to be pretty small. But for here, I don't know the chances we're making this mistake. I will give you this, it's less than 50%. It's not a coin flip here. All right, so that's your first t-test. Kim Shepard's going to be back, do a couple more examples. And as we get close to the end of the book, these should be coming easier. Ask questions if you've got them in class. Thanks for watching, and we'll see you next time.